In this final video on correlation, we'll review some things that can influence the size of a correlation coefficient. There are a number of different factors that can influence a correlation coefficient. For example, let's assume we have a sample with a modest positive association. Outliers, scores that fall far outside the overall distribution of the other observations, can inflate a correlation coefficient if they follow the same general direction as the other scores, but simply fall well above or below the overall range. As we see here, the correlation will look and be stronger if we have one outlier that is large on both x and y. Outliers can also artificially reduce the size of a correlation coefficient if they fall outside the range of the other scores, but in a different direction as the rest of the observations. By adding a case that's very low on x but very high on y, the correlation here will drop. Another thing that will reduce the value of a Pearson's R is a restriction of range in the variables in question. For example, in this case, by examining the association between x and y across a fairly broad range of values, we see a fairly strong association and a relatively large correlation between x and y. However, if we decide to only focus on the upper end of this range, maybe only focus on the highest quarter of scores on x or so, this strong association evaporates, and we see almost no relationship, and thus a correlation close to zero. This can happen all the time in research. We intentionally or unintentionally only focus on children from higher income families or from families with lower levels of education, or children who are struggling with reading. By focusing only on one end of a range of scores, you can end up with a correlation that's a lot smaller than you would see if you randomly sampled from the entire population. Another situation is where you have a curvilinear or nonlinear relationship between your variables. Pearson's R assesses that straight line linear association. Even a very obvious and very strong U-shaped association will be missed with Pearson's R. Now, if it's curved but still has an overall positive or negative trend, maybe it's U-shaped but dips more at one end of the scale, you may see a small correlation that reflects that trend. But even so, the Pearson's R will suggest that it's a straight line trend and won't say anything about the reality that it's curved. Now, before we wrap up our discussion on covariance and correlation, there's one final observation I want to share with you regarding correlation coefficients. To do that, let's look at a hypothetical example of the correlation between child sex and autism diagnoses. Now, I know that these are not continuous variables, but it will help simplify the concept that I want to introduce. Let's use this grid to illustrate the relationship between child sex and autism status. If I think that child sex is related to autism, specifically that males are more at risk for having autism, what would be the strongest possible correlation that I could see? Well, the strongest association would be where every female child was in the not identified group down here, and every male was in the identified with autism group up here. But it's not that simple. What if only 1 in 100 children have autism? I know it's more than that, but let's keep the math simple. In that case, let's say I sample 1,000 children, half male and half female. What's the largest effect I could see? Well, like we just said, every single female would need to be in the not identified group, all 500 of them. Okay, what about the males? Well, if I have 1 in 100 with autism and I have 1,000 children, I expect 10 children to have autism. The strongest possible effect would mean that every single child with autism is also male, all 10 of them. But that's only 10 of 500 male students. Where are the other 490 male students? They're all down here. They don't have autism. Clearly, this does not look like a strong correlation. In fact, if you calculated the correlation, it would only be an R of about 0.101, a small correlation based on Cohen's guidelines. Remember, this is the largest possible effect that you could see with this data. You can't get a larger effect than every child with autism being male and no females having autism. And it's still only a correlation of 0.101. What's going on? Now, it's not a failing of the math or of the correlation coefficient. It's just a result of two distributions being very, very dissimilar. One variable, child gender, is a 50-50 split. On the other hand, the other variable, diagnosis with autism, is 1 to 100 split. The two distributions are very different. When you have very dissimilar distributions, the correlation coefficient can mathematically be capped at values less extreme than 1 or -1. Because this example didn't use continuous variables, it's a little more obvious. But the issue applies even with continuous variables if the distributions are very different from each other. The key here is that it's not a problem with the correlation coefficient. It's just that a correlation coefficient isn't always the best way to measure or capture the strength of some association. In fact, in this case, the value you would get if you calculated something called a risk ratio would be infinity, and you can't get bigger than infinity. In that case, that would be a better way of assessing the strength of this relationship. To use that old analogy, don't try to make the foot fit the shoe. Get the right shoe. Use the right statistical tool for the job. We often fall into a habit of using the same techniques over and over again, but don't fall into that trap. Develop a larger toolbox of statistical instruments that you can use for different situations, and then use the right tool for the right job. Okay? Now, that wraps up our conversation on covariance and correlation. Bye for now.